seemed like the easiest way to explain the assignments that I have given my students in GeoGebra this year, and at the same time show the work that they've submitted. You're looking at a GeoGebra that was submitted about the linear function by a student whose initials are AB. Here's another one on the absolute value function. Here's one on the quadratic. Same initials, but different student. And here's one on the square root function. In each case, the students had to create sliders, and that's these things over here, that would control the parameters for the function. So for the linear function, this slider here controlled the slope, and this one controlled the initial value. For the absolute value, there had to be an A parameter, and an H and a K parameter. Same three parameters for the quadratic, A, H, and K. And the square root function had to have 4 parameters. That would only work if the function rule itself was input properly. So for the linear one, it would have to be typed in as AX plus K. For the absolute value, it would have to look like that. Otherwise, the sliders wouldn't work the way they're supposed to. For the quadratic, it would look like this. And for the square root, 4 parameters, and all 4 of them had to be in there in the right order and with the right brackets. They also had to display the current 0 and y-intercept of the graph and its coordinates, and that had to remain accurate regardless of what the current function was. So, for example, the 0 is here for this particular function, but if I change the parameter A, the 0 changes, and that should be accurately reflected here. Same thing for the absolute value function. 2 zeros in this case, and they had to be accurate, and the y-intercept. Again, regardless of how I change the parameters, it should remain in the right place. Same thing for the quadratic. Same thing for the square root function. It all had to be accurate for whatever the current function was. In order for that to happen, they had to figure out, first of all, a formula for the y-intercept, for example, and type that in using the parameters. So there's the formula for the y-intercept of the linear function and the formula for the 0 of the linear function. Here they are for the absolute value function. Here's one of the zeros for the absolute value. Here's H minus a bunch of stuff. And here's the other one, H plus a bunch of stuff. Now, not only did they have to put these formulas in, but they had to figure them out. So there's the 0, one of the zeros for the quadratic. Here's the other one. And here's the y-intercept. And here they are for the square root. Here's the y-intercept. And here's the 0. The next layer of complexity to add was conditionals. This student is displaying right now the message that this function is decreasing. However, if I change the value of the slope so that it's positive, now the message that's displayed is this function is increasing. So the student had to go into the properties for this text and tell GeoGebra under what conditions he wanted this message to be displayed, under the condition that A is a positive number. Another place where the conditional features of GeoGebra came in really handy was for the square root function, which sometimes has a 0 and a y-intercept, but not always. For example, if I make k positive, you can see that there is no 0, and so the students had to tell GeoGebra under what conditions to display a message like this, that there is no 0. Because for some functions, like the square root function and the absolute value function, GeoGebra will continue to display those points even though we know that they don't exist. So once again, the students had to tell GeoGebra under what conditions to display a message like there is no 0. And for that, they had to figure that out. The final element that I wanted in these assignments, and this was something in common to all 4, was that each one have a point P sitting right on the function curve, that would move with the t slider. In this case, the student had the trace feature on as well. You see the point moving along the absolute value function, along the quadratic, and along the square root. But in this case, I use the fact that the point itself doesn't even show up until the t slider enters the domain of the function. In order for that to work, the point P in each case had to be defined by an ordered pair whose x-coordinate was t and whose y-coordinate was the function with the x replaced by t. So that's how it looks for the linear. There's the absolute. There's the quadratic. And there's the square root.